So this part of the lessons deals with the motion of a charge between parallel plates. And for this, we will divide it into two parts. Part one is when the charged particle is entering collinear with the electric field strength between the plates. So this will be part one. Charge is collinear with the electric field strength between parallel plates, and part two will be when charge is entering perpendicular to the electric field strength. We'll probably will have two videos for this, but let's see the first part here. Okay, so let's suppose that we have two parallel plates that looks like this, that have a hole in one of the plates, and then the this is the negative plate and this is the positive plate, and an electron is entering, is just entered, released through the hole on this situation, parallel plates. Now the change of voltage between the parallel plates is of 100 volts, and let's say that the distance between the two plates is 3.0 times 10 to the power of negative 3 meters. And what we are looking for is that since the electron is released from the hole, meaning that the initial velocity of the electron is equal to 0, because the word release gives that away, and we are looking for what is the final velocity of the electron as it is reaching the other plate here, positive plate. Now we have studied even before that the natural flow of the electron will be to go toward the positive plate. And now when we are dealing with the charge moving collinear with the electric field strength, it's the easiest way is to use the conservation law of energy. You can use kinematics here. However, I suggest using conservation law of energy. Conservation law of energy is saying that in an ideal system, the energy is conserved, is not destroyed, is not created, but it is transformed from one form to the other. So now, when the electron is entering, so we have a initial, we have an initial situation or initial situation of the electron in this case, and then we have a final situation of the electron. So now, as the electron is released, that means that the kinetic energy of the electron is equal to 0, because the initial velocity or speed of the electron is equal to 0. And as it is entering in between the two parallel plates, what it is facing is a change of the electric potential energy that the electron possesses at this point here, because it is between the two plates. And now, as it is moving toward the other plate, what is happening is this initial energy, mechanical energy, but some of the energy of the system is transformed into the final kinetic energy of the electron. So the conservation law of energy on this case will be written as kinetic initial plus electric potential of the electron initial is equal to kinetic final. Now, since it is released there, then what do you have is that the um, electric potential energy is equal to kinetic final. Now, electric potential energy is the change of voltage times the charge, and this will be 1 over 2 mass V final squared of the electron. Now, the charge of the electron is 1 elementary charge, so this will be delta V times elementary charge is equal to 1 over 2 mass of the electron is given. It's in your formula sheet, and V final squared. From here, V final will be the square root of 2 times delta V times elementary charge over mass of the electron. Now, in our case, delta V was 100. So V final will be the square root of 2 times 100 times elementary charge is 1.60 times 10 to the power of negative 19. The whole thing over 9.11 times 10 to the power of negative 31 kilogram, which is the mass of the electron. So enter this in your calculator. Do not forget to square root it. And just keep in mind that the velocity cannot be greater than the speed of light, because nothing exceeds the speed of light. And hopefully those numbers will give us that it's not exceeding the speed of light. So we'll have 5.93 times 10 to the power of 6 meters per second. Okay, so the final speed that the electron is hitting that positive plate will be 5.93 times 10 to the power of 6. Now, when you have a question on the diploma or on the test, what you will see is write or find the final velocity of the electron and write it on the form A dot BC times 10 to the power of D meters per second, and record only A, B, C, and D. What you have to do is here you will place whatever is the A variable or A digit, and on the second B, and on the third D, and on the fourth D, and on the third C. So in this case, what you will record will be 5, 9, 3, and 6, and no units or no anything else. So let's take a look at a second example when we have an alpha particle. So example 2. Again, we are in the situation that we have parallel plates, and now this is negative and this is positive, and then we have an alpha particle that is released again. And the change of voltage between the two parallel plates is 150 volts. Now, as you even noticed from the previous example, we don't even need the distance between the two parallel plates, because as I said, we are using here the conservation law of energy, not kinematics. And if we were using kinematics, then you would need the distance between the two. So the conservation law, now before we move to conservation law of energy, the fact that it is released means that the initial velocity is 0. And then what do we have in terms of the charges? The charge of the alpha particle is 2 elementary charge, and it is positive. Then we will have positive 2 times 1.60 times 10 to the power of negative 19 coulombs. So the charge of the alpha particle is 3.20 times 10 to the power of negative 19 coulombs, while the mass of alpha particle in your formula sheet is 6.65 times 10 to the power of negative 25 kilograms. I think it is 25. Let me double check if maybe it's 27. Yes, it is negative 27. Okay, so now again, since it is starting from rest, then kinetic energy of the object before it is 0, so will be just the electric potential energy that the particle possesses. And now we know that it possesses because the natural flow of the alpha particle is to go toward the negative, and this is transformed into kinetic final. So that will be delta V times Q equals to 1/2 mV final squared, since the initial is equal to 0. Now this is, if we are just doing the literal one, we'll find that the V final being equal to 2 times delta V times charge of the alpha particle over mass of the alpha particle. So if we replace what we have here, 2 times 150 times 3.20 times 10 to the power of negative 19 over 6.65 times 10 to the power of negative 27 kilograms. And then if you enter this in your calculator, you will see that it is 1.20 times 10 to the power of 5 meters per second. So this is what it is happening with the what is it? Can you open your mic and talk to me? Yeah. Why though? Just try it, and if not, then I will extend. Okay, let me know before, like, let's say at 10:30 if you want to extend. So again, when we are working with the energy on the part where the particle is moving collinear with the electric field, then it's easier than working using kinematics. So let's see now a case when the particle that is entering between two parallel plates is having a certain velocity. So it is kind of having a start with the velocity. So the example that we will see now will be when we have a proton that is entering between two parallel plates of proton, and the initial velocity of proton is 2.50 times 10 to the power of 3 meters per second. Now we have a change of voltage here that is 120 volts. And this is positive plate and this is negative plate. Now, proton being a positive charge naturally will fall into the negative plate or the lowest voltage plate. So what do we see in this case is that based on the conservation law of energy is that you now have a initial kinetic energy, and then as proton is entering through the positive plate and is naturally falling to the negative plate, will have an electric potential energy that proton is possessing, and this will be equal to the final kinetic energy. So this is how we write the conservation law of energy on this case. Now, the previous cases, kinetic energy was equal to 0. Now we do have mass of the proton, initial to the power of 2 plus electric potential energy is delta V times Q, and this will be equals to mass of proton V final squared. Now we know everything here, but the final the speed of the proton. Now, even though that the problem is not giving you the mass of the proton and the charge of the proton, you have that. You can find them into your formula sheet. So in your formula sheet, you can find that mass of proton is 1.67 times 10 to the power of negative 27 kilograms, and charge of the proton is 1 elementary charge. Now, which means that is 1.60 times 10 to the power of negative 19 coulombs. So if we want to go with the literal equations, then we find that the final squared is equal to the square root of 2 times 1 over 2 mass of the proton V initial squared plus delta V times charge of the proton, the whole thing divided by mass of proton, and then the result is square rooted. And if we want to substitute, then we'll have 2 times 1 over 2 times 1.67 times 10 to the power of negative 27 times speed was 2.50 times 10 to the power of 3, the whole thing to the power of 2 plus 120 times 1.60 times 10 to the power of negative 19. And the whole thing is divided by 1.67 times 10 to the power of negative 27. Make sure that you are using brackets if you have those old calculators, or that fraction option that we have discussed class in terms of the newer versions of the calculator. So now when you enter it in your calculator, the final velocity will be 1.52 times 10 to the power of 5 meters per second. This will be the final velocity as it is reaching the plate, the negative plate. And of course, you are expecting that the final velocity will be higher value than the initial velocity. And because what it is happening is that the proton in our case is naturally falling to the negative plate. So there is no resistance into proton being a positively charged particle moving toward the negative plate. Okay. Now let's see, we will refer to this because I want to ask you what will happen if you switch the polarity. So now the negative plate becomes positive and the positive plate becomes negative. But before we do that, this is for your homework, I will suppose. But then let's see when we have an alpha particle that is entering between two parallel plates. So now this is negative plate and this is positive plate, and an alpha particle that is entering with an initial velocity of 2.50 times 10 to the power of 3 meters per second. And the change of voltage is 120 volts. And the distance between the two is 5.0 times 10 to the power of negative 3 meters. So now the question will be, this is more complex question. The question will be, will it reach, alpha particle, will it reach the second plate, the other plate, in this case the positive plate? Will it reach it? And if it does, what is the final velocity? If it doesn't, where is it stopping? So the delta D is this one here. Again, so will it reach the plate, the other plate? If yes, what is the final velocity? If not, where is it stopping? Okay. So in order for the alpha particle to reach the other plate, the positive plate on this case, so this is not a natural flow, because the alpha particle, being a positively charged particle, will naturally go to a negative one. But in this case, what is happening is that alpha particle is moving against the electric field strength that the plate has, because see what we have here. So here proton is going along with the parallel plate, and proton is positive charge. Alpha particle is in the same direction, and this is very similar to you dropping an object from a certain height. So this example here is the same as dropping an object from a certain height in the gravitational field. All those examples here, even the electron, because the electron is negative charge and the field is the opposite of the motion. Okay, so however, on this case, what do we have is the same, you throwing an object straight up. So the gravitational field is the opposite direction of the gravitational field is the opposite direction of the motion of the object moving. And in this situation, you will see if it stops. And if it stops, where will it stop? So will it be greater or less than the maximum height in that analogy with the gravitational field? Will it be greater than the maximum height or not? This is what is the analogy with. So now the conservation law of energy will be, in this case, will be that we have initial kinetic energy, and then the gravitational potential energy is actually opposing the motion of the particle. Okay, so let's write now the conservation law of energy. That will be initial kinetic minus the electric potential energy. This will be equals to kinetic final. However, since we are taking away the electric potential energy, because the electric potential energy is working against the motion of the particle, let's see and compare those two together. So is kinetic energy greater enough to overpass the electric potential energy? In other words, is the left side of the relation for the conservation law of energy positive or negative? And if it is positive, that means that kinetic energy is larger enough to overpass the resistance that the electric potential energy is having on this case. So mass of the alpha particle is 6.65 times 10 to the power of negative 27 kilograms, and charge of alpha particle is 3.20 times 10 to the power of negative 19 coulombs. So what we will have in this case is the left side will be 1/2 mass of alpha particle, the initial squared, minus delta V, which in our case is 120 times charge of alpha particles. And see, if this is positive, that means that kinetic energy is greater than electric potential energy. So you are able to overcome the resistance that the electric potential energy is having into the particle and reach the other plate. And if it is negative, then that means that initial kinetic energy is less than electric potential energy, which means that the initial kinetic energy of the particle is quote unquote eaten up by the electric potential energy between the two plates. That means that the particle will not reach the other plate. Okay, will stop. The path of the particle will be something like this. Well, go up to a certain point and then we'll come back to the plate where it started to move. Okay, does it make sense? So the negative number of the left side of the conservation law of energy is telling us is that the particle will not reach the other plate. And if it is positive, that means that you have enough kinetic energy to overpass the resistance that the electric potential energy is having. Okay, so let's do the calculations here, and let's see. 1/2 times 6.65 times 10 to the power of negative 27 times 2.50 times 10 to the power of 3, the whole thing to the power of 2, minus 120 times 3.20 times 10 to the power of negative 19. And this in your calculator will be negative 3.84 times 10 to the power of negative 17 joules. So the fact that is negative means that we are in this case where the particle doesn't have enough kinetic energy to overcome the resistance that the electric potential energy is exerting and make the particle to move to the other plate. So now let's figure out what is the distance that it stops. Meaning that we will what is the voltage? What is the voltage that makes the final kinetic energy or makes the object to stop? Okay, what is the voltage that makes the object to stop? So we have 1/2 mass of alpha particle, initial velocity squared minus the change of voltage that it stops, charge of alpha particle. This is equal to 0. So now from here, 0 because it's stopping, and then we will find that change of voltage here. Okay, where it stops. And it stops means that the kinetic energy at that point is equal to 0. So now the change of voltage where the particle will stop will be equals to 1/2 mass of alpha particles times initial velocity squared over the charge of alpha particle, or 1/2 times 6.65 times 10 to the power of -27 times 2.50 times 10 to the power of 3, the whole thing to the power of 2 over 3.20 times 10 to the power of -19. So enter this in your calculator and then we'll see what is that voltage. I have here 0.065 volts. Now this will give us the voltage. Let's see now what is the distance that it is stopping. Now this, for the easiest way to go in this case will be that you have the fact that the magnitude of the electric field strength between the two parallel plates is a constant value, is a uniform one. So it's uniform, and it is delta V over delta D. So now if when it is the whole thing, 120 over delta D, that is that 5.0 times 10 to the power of 3, then is the same as delta stop over delta D hold stop. And this is the easiest way that I found out to do, but you can go even with kinematics. 0.0625, 65, not 625, 65 over delta stop. When you have a ratio like this, it is cross multiplied to that you know, and divide by what is left. So 0.065 times 5.0 times 10 to the power of -3 over 120 volts. And the volts is cancelled, and then we have meters. 2.71 times 10 to the power of -6 meters. Okay, so this is how you deal with those questions, and we'll see more questions like this when we are in class. Now, what I want you to do is to revisit the previous example and then just say what will happen if we switch the polarity. So now this is becoming positive plate and this is becoming the negative plate. What will happen? And the same thing, you will discuss the same thing. So will it reach the plate? If yes, what is the speed? If not, where will it stop? Okay, so we'll see more examples like this in class, and I hope that this makes sense.